Before there were stars, before atoms, before light, there was a silence so absolute, physics still doesn't know how to describe it. Because the Big Bang isn't the beginning the way people picture it. It's the oldest page we can still read, and everything earlier looks like it was erased on purpose, by the limits of space-time itself. And yet, the universe left breadcrumbs, a ghost signal in microwaves, a sky-wide afterglow, a temperature map so precise it feels like a fingerprint. So tonight, we're not asking how the universe began. We're asking the question that makes cosmologists go quiet. What came before the Big Bang? Welcome to Void Therapy. Let's clear the biggest misunderstanding first. The Big Bang is not a bomb that exploded into empty space. It's the name we give to one specific fact. The universe used to be hotter, denser, and more compressed than it is today. And it has been expanding for 13.8 billion years. That's it. That's the core claim. But then school does this sneaky thing where it adds a cinematic ending. Everything came from a singularity. Time begins, nothing before. And it sounds final, like a locked door. Except modern cosmology doesn't treat that door as locked. It treats it as unopened. Because when you run the equations backward far enough, physics starts screaming. General relativity, Einstein's masterpiece, works unbelievably well on planets and galaxies, but it was never designed to describe reality at infinitely small scales, where quantum mechanics rules. So when people say, the Big Bang is the beginning, what they often mean is, our math breaks before we can see earlier. And that's not the same thing. So what do we actually know is true about the Big Bang, like solid, bet your reputation true, and what parts are still just educated guesswork? We know the Big Bang happened because the universe left receipts. First, the expansion. In the 1920s, Edwin Hubble helped confirm that distant galaxies are rushing away from us, and the farther they are, the faster they recede. That's not galaxies moving through space like bullets, it's space itself stretching. Second, the early universe chemistry. When the universe was minutes old, it was hot enough to fuse light nuclei. That early phase predicts a specific mix of hydrogen and helium, roughly 3 parts hydrogen to 1 part helium by mass, plus a tiny sprinkle of lithium. And when we look out into ancient gas clouds and the oldest regions of the cosmos, the ratios match astonishingly well. Third, the afterglow. In 1965, Arno Penzias and Robert Wilson found a stubborn microwave hiss that wouldn't go away. That hiss turned out to be the cooled, stretched relic light from the early universe, the cosmic microwave background, a near uniform glow at about 2.7 Kelvin. Later satellites mapped it in exquisite detail. And that map wasn't just pretty. Those tiny temperature ripples are the seeds that gravity later grew into galaxies, clusters, and the cosmic web. So yes, the hot, dense, early universe is real. But here's where it gets spicy. That evidence doesn't prove a beginning from nothing. It proves that there was a hot, dense phase we can trace back to. And now we can answer the real question hiding under the question. When you say, what came before the Big Bang, you're really asking, what caused the hot, dense phase? What set the initial conditions? Okay, so if we can't trust our math all the way back, why does everyone talk about a singularity like it's a confirmed thing? Because a singularity is what happens when you push a theory past its warranty. In the 1960s and 70s, Roger Penrose and Stephen Hawking proved powerful singularity theorems. Under certain assumptions, like gravity behaving normally and space-time behaving smoothly, an expanding universe traced backward tends toward a breakdown point. In simple terms, general relativity predicts its own failure in the extreme past. That's important. It's not necessarily predicting a literal point of infinite density. It's telling you, you need new physics here. And that's where the leading idea enters like a plot twist. Inflation. In inflationary models, the universe undergoes an absurdly fast growth spurt in a fraction of a second, driven by a high energy field. That burst helps explain why the universe looks so geometrically flat on large scales and why distant regions of the early universe share nearly the same temperature. But inflation also creates a weird possibility. The Big Bang might not be the beginning. It might be the moment inflation ended in our region, when that field's energy converted into the hot soup of particles and radiation. In that picture, before the Big Bang could be an inflationary phase, an earlier chapter where space-time already existed, expanding silently. And then there are the more radical contenders. Bounce models. The universe contracts, reaches an ultra-dense state, but not infinite, and rebounds into expansion. Some versions appear in approaches to quantum gravity, like loop-inspired cosmologies. Ekpyrotic/brain ideas. Our Big Bang could be a collision or interaction in a higher dimensional reality. Cyclic universes. Expansion and contraction repeating, with each cycle leaving faint fingerprints. And if you want the truly mind-bending one, eternal inflation/multiverse. Inflation may not end everywhere at once. It could continue out there, spawning many bubble universes, each with its own Big Bang-like beginning. But we don't get to pick the coolest story. We pick the story that leaves testable scars. So how do you test something before the earliest light we can see? What evidence could possibly survive? We test the before by looking for the faintest consequences it would leave on the after. The cosmic microwave background is our baby photo of the universe, captured when atoms first formed and light finally traveled freely, about 380,000 years after the hot phase began. We can't see earlier than that with light, but we might detect patterns that earlier physics imprinted into space-time itself. Here's what scientists look for. 1. Primordial gravitational waves. Inflation-like models can produce ripples in space-time. Those ripples would leave a specific twisting pattern, B-mode polarization, in the CMB. Detecting a clean primordial signal would be a massive clue about what powered the earliest expansion. 2. The shape of the primordial noise. Those tiny CMB fluctuations follow statistical patterns. Different before scenarios predict different kinds of distributions: how smooth, how lumpy, how correlated across scales. 3. Large-scale anomalies and structure. If there was a pre-Big Bang phase, it might leave subtle weirdness in the largest patterns we can measure: how galaxies cluster, how the cosmic web formed, how uniform the early universe truly was. And this is where we land on the honest truth. Right now, the Big Bang is a solid description of an early, hot, dense epoch. Inflation is a powerful idea with strong explanatory winds, but still under scrutiny. Bounce and cyclic models are intriguing, but harder to confirm. So what came before? It's simple. We don't know yet. But we're no longer guessing blindly. We're narrowing the suspects by evidence. And that's where it turns philosophical. Because this question does something to people. Maybe the universe isn't asking us to find a single first moment. Maybe it's forcing us to confront a deeper idea, that reality might not be built like a story with a clean opening line. It might be built like an ocean, where the surface looks like a beginning until you learn to dive. Subscribe for more. Also, YouTube thinks you should watch this one next. Until then, stay curious.